What does it mean to say that a function is differentiable? Well, let's recall our definition of f prime of c. Remember that f prime of c is the derivative of f at c, and it represents the slope of the tangent line to the graph of f at c. And it was defined by way of this limit. Limit as h approaches 0 of this difference quotient, f of c plus h minus f of c all over h. And if this limit exists, we say that the function is differentiable at c. Okay, so if f prime of c exists, right, this limit exists, then the function is differentiable. And what that means is that we have a nice tangent line to the graph. Okay, so the tangent line has some nice slope where the slope is some number. Now, is it possible for a function to not be differentiable at a certain point c? And it turns out that it is. So let's go to Desmos. And notice our first example will be f of x equals the absolute value of x. This function is not differentiable at x equals 0. Okay, it has a sharp corner there. There's no nice tangent line at x equals 0. If it were kind of rounded off at the bottom, then yeah, we could have a nice tangent line with a slope of 0 there, but it's a sharp corner. We don't have a nice tangent line. In terms of that limit, the limit as h approaches 0, well, if we're approaching from the right, remember what we're looking at is not the function values, but actually the slope of the secant line. Well, if we pick a point on the graph and the origin here, the slope between that point and the origin would be 1. So no matter where we're at, the slope would be approaching 1 here. In fact, the slope just is 1 for every value of h there. As we approach from the left side, though, the slopes are -1. And so that limit is not going to exist. The left and right-hand limits are not going to agree, so the limit won't exist. So the function, even though it's continuous here, this is a continuous function, it's not differentiable at 0. And let me modify this just a little bit here. Let's put in a new function. This function is a modified version of the absolute value of x function. And notice we have this point here, 3, 1. Now, we say this function is not differentiable at 3. We don't say at 3, 1. Usually we just say at x equals 3 or at 3, the function is not differentiable, again, because we have this sharp corner. Now, there are other reasons that a function could not be differentiable. For example, if you have a vertical tangent line. Okay, notice at x equals 0, this function has a vertical tangent line. This is the cube root of x function. And so it's kind of like it has an infinite derivative there, but we say the derivative does not exist. When we take that limit, the limit as h approaches 0 of that difference quotient, we'll actually get infinity, right? But an infinite limit, remember, does not exist. So this function is not differentiable at 0. Okay, another way that a function could not be differentiable somewhere is if you have a cusp, okay, like a sharp corner or a cusp. So notice at any other point here, like this point right here, we could look at what the tangent line looks like, or a point over here. But at 1 right here, at x equals 1, this does not have a well-defined tangent line there. So again, even though this is a continuous function everywhere, it's not differentiable at x equals 1. Okay, now another function would be an example like this. Here we have a vertical asymptote at x equals 2. And so this is not going to be differentiable. In fact, imagine trying to draw a tangent line at x equals 2. The function is not even defined at x equals 2. It's not even continuous. We're actually going to have a theorem that says that if a function is differentiable somewhere, then it has to be continuous. So if it's not continuous, then it definitely can't be differentiable. So this is not even continuous at 2, so it definitely can't be differentiable. And same thing with this last example. Here's a function that is not continuous at 5. So it's certainly not going to be differentiable at 5. Imagine trying to draw a tangent line, right, to the graph at this point, right? That wouldn't even make sense. So this function is not differentiable. Okay, now let's go back to our PDF here. So note, differentiability is a stronger condition than continuity. So if a function is differentiable at c, then it must be continuous at c. Or stated another way, if a function is not continuous at c, then it can't be differentiable at c. Oh, and one other thing I should mention, what does it mean to just say we have a differentiable function? Okay, well, to say a function is differentiable, it just means that it's differentiable at every value of c. Okay, now I should say, though, that differentiability implies continuity, but continuity does not imply differentiability. Right, there are continuous functions which are not differentiable, and we just looked at some examples. So f of x equals the absolute value of x is kind of the prototypical example of a function that's continuous. In fact, it's continuous everywhere, but it's not differentiable at x equals 0 because it has that sharp corner.